Hi everyone, my name is Xubo Liu. Today I'd like to share our work on reinforcement learning for multi-agent collaboration, and it's titled Asynchronous Option-Based Multi-Agent Policy Gradient, a Conditional Reasoning Approach. Our team comes from Simon Fraser University and Hawaii, Canada Research Center. Our SFU team comes from Multi-Agent Robotics Lab, directed by Professor Morton. Check out our lab if you are interested in robotics and learning. In this work, we consider a scenario of centralized control of multiple robots. Specifically, we have a centralized controller which receives the input of a combinational observation from all robots and makes the decisions for all robots at the same time step. This kind of framework implies a synchronized decision-making process. That means the controller chooses action for all robots at the same time step. However, in many realistic cases, we may want a centralized controller select actions asynchronously. Consider the case when we want a robot to make high-level abstract actions like human does. For example, we want a robot to open a door to avoid obstacles. Those high-level actions can make the multi-robot system handle more complex tasks, be more efficient and user-friendly. Each high-level action, also known as option, can contain multiple low-level actions. For example, open a door is one high-level action and contains 4 low-level actions. Now we observe an interesting thing. The two robots need to select options asynchronously. That means when the smart robot is opening a door, the husky robot already takes its turn and needs to select a new option to navigate. They are making the decisions asynchronously. It turns out that this asynchronous situation is not good for centralized reinforcement learning. The key problem here is centralized reinforcement learning needs to select an option at the same time step. So what if one robot needs a new option, but the other robots are still executing a current option and do not need a new one? Should we stop all of them and forcibly assign the new option for all agents? Actually, previous work do use forcibly synchronization to solve this problem. The idea is to let some of the agents either delete or extend their options by waiting in order to make every agent's option always terminate and selected at the same time step. But in this way, it breaks the completeness of each option and could lead to inefficient, unstable learning. For example, in the second case, the robot 2 may wait for a long time until robot 1 finishes its option, but it could have done some other useful things than waiting. To solve this problem, we make 2 changes to the data and the policy that's used in policy gradient reinforcement learning. First, we create a new form of trajectory data using soft synchronization, which means we do not affect the original option execution at all, but only collect data at certain time steps when at least one agent finishes the option. For example, here we collect data at time step 1357 to form an option level trajectory and ignore the other time steps. Second, to generate such option level data, we change the option selection policy distribution from joint to conditional distribution, where the conditions comes from that we only select new options for those who need it, conditioned by other robots' ongoing option. Therefore, ongoing options is not interrupted. We apply this new policy distribution to the policy gradient formula for centralized learning. Using this way, the multi-agent decisions can be made asynchronously, efficiently, without interfering with each other. We show this method on 2 multi-robot collaboration tasks. All options has various time steps. The first one is 2 different types of robots, a car and a drone, to collaborate to fill the water for 3 cups in the room as quickly as possible. The car has ability to fill water, and the drone only has ability to explore and inform the water level of the detected cups. So different robot has to learn fully utilize their abilities to choose which cup to reach first to minimize the total time cost. In the second example, we use 3 different robots to pick up the right goals in right order to finish the task as quickly as possible. Similarly, they have varying lengths high-level options to choose. Only choosing the right option at the right order will result in a quick task completion. They have to learn a centralized controller for this. The analysis result of the training reward shows that our method has a better efficiency and peak performance in both tasks compared to the other forcibly synchronization techniques. The significance of our work is that we are able to seamlessly apply existing policy gradient algorithms to an option-based control task, which give us more capability for a wide range of robot control with high-level action.